Okay, so I wanted to do a couple of the homework problems for you for chapter 3. This first one says, according to Master Foods, the company that manufactures M&Ms, 12% of peanut M&Ms are brown, 15% are yellow, 12% are red, 23% are blue, 23% are orange, and 15% are green. Now it does tell us to round our answer to 4 decimal places. So let's look at this problem. Compute the probability that a randomly selected peanut M&M is not brown. So the probability that it's not brown, we use the complement rule. So the brown and the not browns are all going to add up to 100%. So we'd say 1 minus the probability it's a brown. Remember that complement rule? So if we do 1 minus the probability that it's brown, what was brown? 12% are brown. So it would be 1 minus 0.12. Remember the probabilities we typically show as a decimal. So this would be 0.88. Okay? Let's look at part B. Compute the probability that a randomly selected peanut M&M is green or brown. So what you want to remember is our addition rule tells us the or is going to be, we're going to add them. So the probability of green or brown is going to be the probability of green plus the probability of brown. Now, if they're not mutually exclusive, the addition rule tells us we have to subtract off the probability of green and brown, okay? But of course, these are mutually exclusive, so we don't have to do that because that would equal 0. You can't draw a green and a brown one at the same time. So this would be the probability of it being green. It looks like there were 15% green, so 0.15, plus the 12% that are brown, 0.12, will give us 0.27. Okay? All right, part C here is compute the probability that 3 randomly selected peanut M&Ms are all orange. Well, remember, if we're going to pick 3 out, it means we want the probability that the first one is orange and the probability that the second one is orange and the probability that the third one is orange. Well, all 3 are orange. Remember, the and tells us the multiplication rule. So the probability that the first one is orange times the probability the second one is orange times the probability that the third one is orange. So the probability that we get an orange M&M is 0.23. So I'm just going to multiply these. 0.323 times 0.23 times 0.23. Okay, now remember to round that to 4 decimals. We can go ahead and, if I can move this over here, and do 0.23 times 0.23 0.23, and we get 0.01217, right? Okay, and this last one, if you randomly select 5 peanut M&Ms, compute the probability that none of them are yellow. So it's similar to what we did in part C here, where we did the multiplication, because we want the probability that the first one's not yellow, and so that the first one's not yellow, and the second one's not yellow, and the third one's not yellow. You understand? All the way to the 5th one. So we're going to multiply those. So the probability of not being yellow, up here I know 15% are yellow, right? So not yellow is the complement of that. So that's 1 minus 0.15 or 0.85. So not yellow is 0.85. So I have 0.85, whoops, times 0.85 times, and I'm going to do this 5 times, or you can raise it to the 5th power. Make sense? So on our calculator, we're going to do 0.85, and I'm just going to go ahead and raise it to the 5th power. So 4 decimal places, I'd have 0.4437. All right. Okay, this last one then is if we randomly select 5 unit M&Ms, compute the probability that at least one of them is yellow. Well, if you look at part D, we found the probability that none of them are yellow. So it's actually just going to be the complement of this, 1 minus 0.4437 to make at least one of them. That would be 0.5563. Okay? Okay, let's look at the second one that actually gives us what's called a contingency table. The other video I did with the contingency table had, I think, whether a patient had a certain condition. This one is very similar to that. A CBS News poll involved a nationwide random sample of 651 adults. So that's our sample size, okay? 651 adults. Asked those adults about their party affiliation and their opinion of how the U.S. economy was changing. So the results are shown in this table. So one thing you probably want to do first is know what our totals are. So let's go ahead and add up our totals. So for the number of Republicans, we would take 38 plus 104 plus 44. So we have 186 Republicans. That's our row total. So remember, think about these as rows and columns, right? So the Democrats, we had 12 plus 87 plus 137. So we had 236 Democrats. And for neither, we had 21 plus 90 plus 118, or 229 for the none. Now we want to do the same thing for the rows. We want to get those totals. So these are our totals. We're going to have totals down here. So we have 38 plus 12 plus 21, or 71. 104 plus 87 plus 90, or 281. I thought it was the same. 44 plus 137 plus 118, and 299. Okay, now if we total the total rows and the total columns, they both should total to 651. So go ahead and double check that. I'm just double checking that real quickly to make sure I didn't add wrong. Okay, it does. Okay, so now the probability that a randomly selected adult participating in the study was a Democrat. Okay, a Democrat is one of our rows, so we need to look at the total number of Democrats, which is 236. This row right here, and then divide that by our total. Okay, and it does say to round to 4 decimal places, so we would get 0.3625. Make sense? Now it wants to know what's the probability that they think the economy is the same. Well, the same is now a column. So I want you to ignore the better and worse, only look at this column right here. And the total for the same there, the total for the same is 281. And because that's that whole column, then we divide by our overall total sample size. So we have 281 divided by 651, or 0.4316. Okay, now here's a conditional one. I know some of you had some questions about this. This is the probability that they think the economy is the same given they're a Democrat, which means we're looking at the probability that they think the economy is the same, only looking at, this given means we're only looking at the Democrats. So basically the Democrats are in this row right here. So you're only looking at this row. Okay, this row, whoops. This is all we're looking at. You're going to ignore, at least at this point, we're going to ignore this row and this row, okay? We're only looking at the Democrats. So of those Democrats, what's the probability that they thought the economy was the same? So there was 87 that thought it was the same, right? And then our denominator is the row total of the Democrats, or 236. Does that make sense? I know some of you are struggling a little bit with that one. So 87 divided by 236, we get 0.3686. Okay? Now this next one, we want the probability as Democrat, given they think this the economy is the same. So of all the people that thinks the probability or the economy is the same, what's the probability they were Democrat? So what changes here is, whoops, erase some of that there. Now we're only looking at the people that thought the economy was the same. My 281, sorry, I don't know how I did that, but okay. So we're only looking at this column. We're ignoring these other two columns. So the number of Democrats in this column was 87 out of the total people of 281. So we have 87 over 281. Okay, see how that changed? Our denominator changed there. So we have 87 divided by 281, or 0.3096. Okay? The probability that they're Democrat and the same. Okay, so now we're no longer just looking at these columns. Okay, we're looking at everything. So Democrats and the same, we see where those intersect, which is 87, and we take that out of our total. 87 over 651. Okay, the only time your denominator is not out of the total is if you have this given. So we have 87 divided by 651, or 0.1336. Make sense? Okay, let's just do this last one real quick because I know a couple people had questions on this one as well. Use the following probabilities to answer the question, round to 4 decimal places. If we know the probability of A is 0.17, oops, I don't know why I have this twice here. Sorry about that. That was just a typo there. Probability of A is 0.17, probability is 0.73, and A and B is 0.10. What's the probability of B given A? Well, we know the formula for the probability of A and B is equal to the probability of A times the probability of B given A. So if we basically solve the equation for this, because this is being multiplied, we divide both sides by probability of A, right? This gives us a different formula for the probability of B given A. Our formula becomes the probability of A and B divided by the probability of A. I think that was a little tricky. Okay, so that means here's our formula right here, which is the probability of A and B divided by the probability of A, which is 0.10 divided by 0.17. Okay? 0.5882. Okay, makes sense?